imaging now, positron emission tomography. So we're going to compare them to ultrasound scans. So they're two different ways of producing images, and lots of the medical physics questions are these types, comparing and contrasting the two types of imaging. So we're going to compare them in terms of safety and convenience, and also in terms of the information you get. So let's start off with safety and convenience, because there's quite a few points we could make here. So if you have a PET scan, you will need to be in hospital for several hours. They've got to inject you, get you to the machine, and it takes some time to process images. Whereas ultrasound, you can go in, they can get out straight away and produce images almost instantly. So it's a very quick and easy process. A PET scanner will set you back millions, if not 100 million. I think I looked this up online. They're very expensive. An ultrasound is relatively cheap. So they are very easily available. A PET scanner, so we're now moving on to safety, produces beta plus particles, which annihilate to produce gamma rays, which are ionizing, whereas ultrasound produces sound waves, which are not ionizing at all. So ultrasound would be classified as much safer. In terms of the experience for the patient, anyone who's afraid of needles is not going to enjoy PET scanning because you inject it, and anyone who's claustrophobic again is not going to enjoy a PET scan because you are very close in when you go into the detector, whereas an ultrasound, the only problem might be that they put a gel that might be a bit cold, so there's really not many disadvantages or discomforts for the patient. Okay, so now let's look at the information available. So a PET scanner produces very detailed images, and it particularly images for the metabolic activity, which is why we use it for diagnostically when we're looking at cancer, because it tells us where very active cells are, which is a characteristic of a cancer cell. Whereas ultrasound we use for looking at the boundaries inside us. So we can't really tell how something's behaving, we can just look at what something is. So, oh, here's a bone, or oh, here's a baby, something like that. And the images it produces are pretty blurry. But on the flip side of that, it's very easy to distort or ruin the images with a PET scanner. The patient must lie perfectly still, whereas an ultrasound can easily deal with moving patients. This is how it can see a baby even though it's moving around inside the mother's body. So those are some of the points that you would need to make to answer this question. I gave more than enough for this one, just to show you the different options. Okay, so looking at ultrasound in more detail, we'll take a look at the transducer you'd use in an A-type scan, where you'd measure like bone thickness or retina thickness, something like that. So all we need to do is, referencing the diagram, describe the process we use to produce a short pulse of ultrasound. So we're not interested in the detection part, we're just looking at producing it. Okay, so there's a few key parts. So we're going to have to apply an EMF to the electrodes, and you can see we've done that because we've got a cable coming in supplying the AC EMF. And we're going to need it at a pretty high frequency, so it produces ultrasound. So it needs to be above 20,000 hertz, so above the human hearing range. And then what we're going to do is, when we apply the AC EMF to the electrodes, it's going to cause the crystal to expand and contract. That's why it's described as being a piezoelectric crystal. It can transfer between the electrical energy and elastic potential energy if it's changing its shape. And we pick a crystal specifically with a resonant frequency above 20,000, so that when we supply it with a 20,000 EMF, it's in resonance, so it produces a large pulse of sound wave, which is what we're looking for there. So those are the points I'd make here. Okay, so now we're going to model it mathematically. So we've got ultrasound incident on a boundary between materials, and we've got this equation to work out how much is reflected by the boundary. So what it wants us to do is calculate the amount of ultrasound which would be transmitted by the skin if it were to go through an air-skin boundary. So this equation calculates the amount reflected, so if we want the amount transmitted, we need to do 1 minus it. And what I've done is I've made both of the numbers to the times 10 to the 6. So those cancel out and we don't need to factor them in. So that's what I've done. I've put the numbers in and we can see that we get a very low percentage transfers, 0.052%. Okay. So when we're obtaining the image, we use a coupling gel. So explain why a coupling gel is needed and state the property of the gel that ensures a good quality image. So the coupling gel is to fix the problem we just identified, that none of it's transmitted. So we use the coupling gel to displace any air between the transducer and the skin. So we get rid of the problem of low transmission, and we pick a coupling gel that has an acoustic impedance as close as possible to skin, so we get maximum transmittance or minimum reflection. So they all go into the